Okay, thank you. So hello, everybody. So welcome to this DFT course for the ISTPC school. So let me start by giving you some supporting documents that are useful for this course. So first, I have lecture notes that were written for the previous editions of this school. So you can find it at this address. The link is also in the chat window. And also, I have a more recent review article that you can find on the archive website. And the link is also in the chat window. And so this article overlaps partly with the lecture notes, but it contains more mathematical details because it was written for a book which was edited by applied mathematicians. And in this lecture notes, well, in these lectures, I will try to follow more this review article. So the course will be in two parts. Today will be basic theory of DFT. And then next week, this will be part 2, where I will focus more on the actual approximations used in practice. Okay, so I don't have any slides. I will write everything on the tablet. And for this reason, unfortunately, I need to switch off the video because otherwise you won't work. Okay. Of course, you can stop me whenever you like and ask questions in the chat window. Okay, so let's start with the part 1 of the course. That is the basic theory of DFT. Okay, so I hope everything is working, that you see well. Let me know if it is not the case. Okay, thank you, Emmanuel. Okay, so the first thing is that I would like to review briefly what is the many-body problem in quantum mechanics, also to give you the notations that I will use. So of course, the starting point is that we deal about n-electron systems. So I will mostly think about an atom or a molecule, but possibly it could be also a solid. I will work in the Born-Oppenheimer and in the non-relativistic approximation, as in the previous lectures. And the starting point is the expression of the electronic Hamiltonian. Okay, so I will give you the expression that you all know, of course, but it doesn't hurt to write it again. So I will give it in atomic unit. So this is, of course, so there is the kinetic energy term where you sum over the electrons. So this is the Laplacian with respect to the coordinates of electron I. Then I have the Coulombic electron-electron repulsion. I sum over I sum over J, and J must be different from I of the Coulomb interaction. And I have the external potential, which is the nuclei electron potential. So sum over the electrons of the nuclei electron potential for the coordinate Ri. And of course, the VNE, the nuclear potential, is minus sum over the nuclei that I will index by alpha from 1 to n to n for the number of nuclei, the charge of the nucleus alpha divided by r minus capital R alpha, which is the position of the nucleus alpha. And what we want to do is to solve the Schrodinger equation. So h psi, which depends on space and spin coordinates, x1, x2, xn, equal E psi xn. So I will use this notation. I think it was used also before in the previous lectures. So my notation, xi means a space coordinates Ri and a spin coordinate that I will call here sigma I. I think it was called before omega I, but that's the same. And to be more precise, I will say, so this is a variable belonging to R3 for the space, and for the spins, it belongs to the set with spin up and spin down. Okay. I will also use the Dirac notations. That is the Schrodinger equation. I will write it in practice like this with ket states, and in this case, I will put a hat in, on the Hamiltonian. And the Hamiltonian, to write it in a more concise way, I will write it as the kinetic energy operator T, the Coulombic electron-electron repulsion WEE, and the nuclei electron interaction. I will call it like this. Okay, so now, of course, in practice, we first are interested in the ground state energy of the system. And for this, we have the very convenient variational theorem. Okay, that you probably also know by now. So it says that if you want the ground state energy of the system, you can obtain it by minimizing with respect to an electronic wave function belonging to the space of possible wave function having n electrons that I will call Wn, the expectation value of the Hamiltonian over this wave function. Okay. And let me give you, I told you that I will give you some mathematical details, not too many, don't worry, but let me give you some mathematical details about the space of possible electronic wave functions. So this Wn, it is the set of a wave function that belongs to the so-called set that I will write like this. I'm going to explain what this means. Okay, then it must also belong to the space H1. So this must be to the power n to c, and then it must be normalized to 1. Okay, so that looks complicated, but let me explain exactly what this means. So this symbol is the antisymmetric tensor product. Or I should say n-fold antisymmetric tensor product. So it means, so this part here, let me write in another color. This part here means that I considered some wave function that can be written in the following way. So I have a sum over some indices, one for each electron. So I1 from 1 to infinity, I2 from 1 to infinity, etc. In from 1 to infinity. Then I have some coefficients, Ci1, I2, In. And then I have the antisymmetric product between some orbitals belonging to this L2 squared space. So let's call it phi I1 of x1, antisymmetric product with phi I2 of x2, etc., until phi of In, xn. Okay. And I have the constraint that the orbitals must be different in this product. So I have I1 less than I2, etc., less than In. So this is another name for what you have encountered so far, which is Slater determinants. Okay, antisymmetric product of spin orbitals, and each spin orbital must belong to L2. So it means that if you integrate one spin orbital over all space and spin, then it must be finite if you square integrate it. Okay, so that's what it means. It means that the wave function must be a multi-determinant wave function. Now, the other part here of this space of wave function, it means the following thing. So let me write it here. So the one means that the gradient of the wave function must be integrable, must be square integrable. So it means that if you take the gradient and you square it and you integrate it over all x1, x2, xn, okay, you integrate over R3, the space set, and this is n time, then this must be a finite. And why we need this constraint is to have a finite kinetic energy. Okay. So this is called the Sobolev space. And of course, the last condition is the L2 inner product, which means that the wave function must be normalized to 1. Okay. So this is the mathematical set in which we minimize over the wave function to obtain the ground state energy. Now, DFT is a reformulation of the variational theorem, not in terms of wave function, but now in terms of the one electron density. So let me define the one electron density. Okay, associated to a wave function. So let's say the density rho associated to the wave function psi depends on, let's say, of the coordinate of the space coordinates R1, and it is defined as n, and then the integral of the wave function, the square of the wave function, and I integrate over all the variables except R1. So I integrate over sigma 1, the spin of the first electron, and then I integrate over x2, space and spin of the second electron, etc., until xn. So if I want to be precise here, I will say that I integrate over the spin space of the first electron, and then I integrate over space and spin of the n minus 1 remaining electrons. Okay, and one property of this density is that it is normalized to the number of electrons. So if you integrate the density over all space, R3, it must be the number of electrons. Okay, so basically, now we are going to explain how we can express the variational theorem in terms of rho. Yeah, I need another page. Okay. For some, no, excuse me, I've lost. I don't know why. Don't know why it's doing that. Okay. Okay, so that was the introduction. Now let's go to defining the universal density functional. Okay, and let me talk briefly about the Onenberg and Kohn theorem, which is really the starting point of DFT. So this was a theorem from 1964, okay? And the basic idea is the following. It is, okay, if you are given an external potential defining an electronic systems, so V of R, then you can, of course, solve the Schrodinger equation, and you can find in particular the ground state wave function that I will call just psi, okay? And once you have found the ground state wave function associated with this potential V, you can, for example, compute the density, the ground state density, rho of R. Okay. Now, what Oenberg and Kohn showed is that you can, in fact, invert this process. So if you are given a density rho, you can go back to the potential V, which has rho as a ground state density. So this is the contents of the Oenberg and Kohn theorem. Okay, and since you can find V from rho, it means that V is a function or functional of rho. Okay, so it means that V is a functional. So a functional is simply a function of a function, and since you know V, well, you can compute everything. Okay, so from V of rho, you can know everything from your system. So it means that everything is a functional of the density. Okay. So now I will not show you the proof of the theorem, the original proof, but rather I will give you a more modern approach to this which is equivalent to this theorem, which is the so-called constrained search approach to DFT. So let's talk about that. Constrained search approach to DFT. And I will use that to define what is known as the Levy and Lib density functional. Okay. So the Levy-Lib density functional was formulated by Levy in 1979, and then also by Lib in 1983. And it works as follows. So it starts from the variational theorem in terms of wave function. So I will write it again. So the ground state energy can be written as the minimum over a wave function belonging to this wave function space for n electrons of the expectation value of the Hamiltonian with the kinetic energy operator, the WEE and VNE. Okay. And then the idea is to decompose this minimization in two steps. So in the first step, we are going to minimize over all possible wave function psi belonging to this space, but now with the constraint that this wave function gives a fixed density rho. So now the space is constrained that the density of this wave function must be rho, a fixed density. And in the second step, I minimize over all possible rho. So rho belonging to some space that I will call dn for density, having n electrons. And I minimize what? Well, I minimize the same thing. Okay. Okay, so let me maybe define again with some details exactly what I mean by this space. Okay, so first, this space Wn for fixed density rho, it's easy to define in formal manner. This is the set of wave function belonging to this Wn set, so that the density of this wave function is equal to the fixed density rho. Okay, and I should say that very often in DFT we use more compact notation, and instead of writing that explicitly, we just write this term as psi giving rho. Okay, so you will find this probably many of you have already seen that in the literature. So we write the psi gives rho, which means exactly that psi must give the density rho. The set of density now that you can that represent n electron systems is also known. It's a so-called set of n representable density. So dn is called the set of n representable densities. And okay, it can be written in a formal way by saying, okay, this is the density rho, so that it exists a wave function in Wn, so that the density of this wave function is the same as rho. Okay, so the density belongs to this set if there is a wave function giving this density. This is the n representable density. And it turns out that mathematicians have found more explicitly what is this set. I will give you it here. So this is the set of rho belonging to L1 of R3 to R. So this is the set of functions that you can integrate. So that the density must be greater than 0, of course. It must integrate to the number of electron n. And last condition, again, to get a finite kinetic energy, you need the square of the density to be in the Sobolev space. Okay, so again, it means that that the square of this quantity is sorry, the gradient of this quantity is square integrable. Okay, so anyway, so we know exactly what is this set. And now maybe I'd like to give you a more intuitive understanding of this decomposition. So imagine that we have this set of possible wave function that I will represent like this. And inside this set, I have different wave functions, of course. So I have, let's say, psi1, psi2, psi3, psi4, psi5, psi6, psi7, let's say. Okay. In the first minimization here, this is very simple. I calculate the expectation value of the Hamiltonian over all these possible wave functions, and I look at what is the lowest one. And for example, let's say this is psi5, which gives me the lowest energy. Okay, fine. Now, in the second way of doing this minimization, what do? I first look at what are the wave functions giving me a fixed density rho. So let's say, for example, for this case, that psi1, psi2, and psi3 gives the same density that I will call rho1. Okay, it is possible, of course, because many wave functions, in fact, an infinity of wave functions, can give you the same one electron density. You have much more freedom in a wave function than in the density, so you can have this many wave functions giving you the same density. Let's suppose also that psi4 and psi5 gives the same density that I call rho2. And then let's assume that psi6 and psi7 gives the same density rho3. Okay. Now, when I do that, I fix the density. So let's say I fix the density to rho1, and I minimize over all the wave functions having this density. So I look at this energy for psi1, psi2, psi3. And let's say that, for example, the lowest energy is obtained for psi3. Okay. Now, I change the density. I go to rho2. I look at the minimum for psi4 and psi5. Well, if it is consistent, I'm going to find that it is psi5, which gives the minimum energy for this set. And then I change the density. I go to this rho3 density. I look at psi6 and psi7, and I find, for example, that psi6 is the one giving the lowest energy between the two. Okay. In the last step of the minimization, I minimize over this density set. So now I compare the energy that I obtain with psi3 for rho1. I compare with the energy obtained with psi5 for rho2 and with psi6 for rho3. And if it is consistent with what I've started from, I'm going to find that again, the one minimizing this expression is psi5. So from this, I think you can see that it is exactly equivalent to the original minimization. Okay. So now let's continue after this decomposition, because we can say, okay, in this expression, the VNE part, the expectation value of the weight of over psi, in fact, depends only on the density. And so you can separate it from this minimization. So I can write the ground state energy as the minimum over n representable densities of the minimum of psi having the density rho of the expectation value of T plus WE. And the VNE part, I will extract it and I will put it in another term, and I can write it more explicitly as the potential, the VNE potential integrated over the density rho. Okay, I hope you see that. that I can always extract the VNE part because it depends only on the density, and this minimization is done at constant rho. Well, okay, and once I have done that, I am left with this expression, which is a functional of the density because it depends on rho. So I will call it f of rho. And it is a universal density functional. It is a universal functional in the sense that it does not depend on VNE. And VNE is the thing that that will change from one system to another. But if you keep with electronic systems, T and WEE will always be the same. Okay, so you have a single functional for all electronic systems. And yeah, okay, so let me rewrite the definition. So the Levy-Lib functional is defined with this constraint such expression, and the minimizing wave function, I will call it psi of rho. It is a functional of the density. So I can write the minimum as this. Okay. At the end, I can therefore write the exact ground state energy as the minimum over all n representable densities of this universal functional f of rho plus the electron nuclei, the electron nuclei interaction. Okay. And so you obtain the exact ground state energy of your electronic systems. And at the minimum, the density that minimizes this expression will be the exact ground state density. Okay, so at the minimum, we are going to get rho 0, which is the exact ground state density of your system. Well, if it is not a unique quantity, if the ground state is degenerate, you are going to find one ground state densities. Okay. Okay, so you see what we have done here in DFT. We have started with the minimization over very complicated wave function, multi-determinant wave functions, and we have replaced that by a minimization over simply the density, which is a much simpler quantity. So it's a tremendous simplification, and this is really the beauty of DFT, this simplification. The only issue is that in order to use this expression, you need now an approximation for this f of rho, okay? And the problem is that this f of rho, we don't have good enough approximations to do chemistry. In particular for the kinetic energy part, you know, this f of rho has a kinetic energy part and a potential part. And we don't have good enough approximation. So in practice, we don't do that, but we are going to reintroduce some wave function, and this is the Concham scheme that we come now. Just a remark before we go on to the Concham scheme. Here, the functional, as I told you, is called the Levy-Lib functional. there, there is an extension of this functional called just the lib functional, which can be found from the so-called Legendre transformation, and it can be seen as an extension of this functional where you don't vary over simply some wave function, but now you vary with respect to ensemble density matrices. Okay, so you extend the space for the minimization, and this has the advantage that the functional has a nicer mathematical property like convexity. But this is, I would say, a detail for what we care about in practice. So I will keep with this simpler Levy-Lib functional. Okay, so maybe do you have any question at this point before we continue with the Consham scheme? No, it's fine. Okay, so then let's continue. In another page. Okay. So 3 Consham scheme. Okay. And first, we are going to talk about the decomposition of the universal functional f of rho. Okay, so the idea of Kohn and Sham, which is from 1965, so just 1 year after the Hohenberg and Kohn theorem, was to say, okay, since we don't know good approximation for the entire functional f of rho, we can try to decompose it in different terms. So they decompose f of rho as Ts of rho plus E Archery exchange and correlation. I'm going to explain the definition of this quantity. So first, Ts. So Ts is the non-interacting kinetic energy. And it is defined again with this constraint search approach by doing a minimization. But now it is possible to use a single determinant wave function that I will call phi of the kinetic energy operator. And what is exactly the set of the single determinant? I will call it S for single Slater determinants with n electrons and a fixed density rho. Okay. Okay, and at the minimum here, when you do this minimization, the minimizing wave function, I will call it phi of rho. It is a functional of rho, expectation value 40. Okay, and this phi of rho is called sometimes the Consham wave function, Consham determinant. Okay, so let me give you maybe some mathematical details about this set of Slater determinants. So one way of writing it is the following. So first I define the set of all possible Slater determinants. So space of all Slater determinant. And so what is the definition? Well, this is all the Slater determinant. And again, a nice way of writing a Slater determinant is to say that you have spin orbital, let's say phi 1, antisymmetric product with phi2, antisymmetric product with etc. until the last spin orbital phi n. Okay, and the normalization is included here in the definition of the tensor product. And you have some conditions. So for all I, each spin orbital must be, in fact, a function of the Sobolev space H1, which means that it has a finite kinetic energy. And it can have complex values. And also, you need the spin orbitals to be orthonormal. So for any pair of I and j, the overlap phi 1, phi j is a delta, is a Kronecker delta. Okay, so that's the space of all Slater determinants defined in an appropriate way. And now, of course, what I've used here, it's the space of all Slater determinants giving a fixed density. So it is simply a determinant belonging to this space, so that the density of this determinant is the same as rho. One important remark here is to say that for any rho, even a density that comes from a multi-determinant wave function, you can always find a single determinant giving you this density. So by doing that, you don't introduce a restriction on the possible set of density rho. Okay, so if I can write it in a formal way, it will be like that. So for any rho belonging to the set of n representable density that can come from any possible wave function, including a multi-determinant one, there is always a single determinant, so that the density of this single determinant is the same as the density rho. Okay, so it's an important thing which that we use in practice in Concham in order to keep exact expressions in principle. Okay, so that is the non-interacting kinetic energy density. And the rest here, the remaining functional, is defined by difference. And it is, as the name suggests, it's called the Archery exchange and correlation functional. And it is defined so that it is an exact decomposition. Okay, there is no approximation here. Okay, I see a question in the chat. So are the N representability and the V representability conditions in the minimization equivalent? No. The V representability condition is a stronger condition. It means that a density must not only be represented by a wave function, but you can also find a potential so that the ground state density of this potential is the density rho. In fact, I will come back to the V representability condition in a moment when we try to take functional derivative of the functional. But at this point, we are concerned simply about the N representability condition. Okay. I should say also that in the original proof of the Hohenberg and Kohn theorem, they used the V representability condition. And thanks to Levy and Lieb, with this constraint such approach, we don't need anymore this V representability condition, at least at this level. We simply need the N representability condition. Okay, so let's continue now with this decomposition. So you see, the idea is that since the kinetic energy part of F is difficult to approximate in practice, the idea of Concham is to do this this decomposition and to express a big part of the kinetic energy in this way, using explicitly a wave function, a single determinant, a wave function. And we are not going to make any approximation on TS. We are going to use exactly this expression, and we are going to use approximation only for the remaining part, the Archery exchange correlation part. Okay, so let's how it works. So what we need is simply to introduce this decomposition back in the in this expression. Okay, so let's do that. So I can write the exact ground state energy as the minimum over all n representable density of Ts. So Ts, I will write it explicitly in terms of minimization over Slater determinants, giving me the density rho. Then I have the Archery exchange correlation functional of rho, and then I have the VNE integrated over the density. Okay. Now I can do something, which is I can recompose these two minimization step in a single one, because I can play a trick here. Here, this is rho, but the Slater determinant phi is constrained to give me this same rho. So here, instead of having rho, I can equally have phi, rho of phi. That is the density coming from this phi. That's the same rho. And here as well. And by doing that, I can put the parentheses here. I can view all this as a functional of phi, of the single Slater determinant. Okay? And once I have done that, then I can recompose the two-step minimizations in a single one. And if I do that, I'm going to get that it is the same as the minimum over all possible Slater determinant of phi t. And here I will do something to simplify the expression. The VNE part, I can put it back now in the expectation value. So I will put the VNE operator here. It is exactly the same. And now I have the Archery exchange correlation functional depending on rho of the determinant phi. Okay? And so this is the Consham expression. Now, this expression again gives you the exact ground state energy. It doesn't give you the exact ground state wave function because the minimizing wave function will be a single Slater determinant, and we know that the exact wave function is not a single determinant. But nevertheless, the density associated to the minimizing wave function here will be the exact ground state density, or one of the exact ground state densities if it is degenerate. Okay. So again, you get the exact ground state energy and the exact ground state density. So you see from where we started with the minimization over a multi-determinant wave function psi, and now we arrive at not a minimization over density, but over single Slater determinant. And even though we still have a wave function, it is a much simpler wave function. Okay, so it is still a great simplification, this Consham scheme compared to the original variational theorem. And in fact, it is quite similar to Archery-Fock theory. Okay, so in Hartree-Fock theory, you estimate the ground state energy by about the same expression where you minimize with respect to single Slater determinant. And you minimize what? Well, the expectation value of the Hamiltonian. So T plus VNE plus WEE. But because of the presence of these two-body interaction, this is only an approximation to use a single Slater determinant. So here you obtain the Hartree-Fock energy, which is greater than the exact energy. But you see in DFT, we use the Slater determinant only to compute the one electron part of the Hamiltonian. And for the two electron part, we have replaced it by a functional of the density. And since the density can be represented by a single Slater determinant, then it is still exact. Okay. So that's a trick that allows you to give to have the exact energy, even though you use only single Slater determinant wave functions. Now, let me talk about the R3 exchange correlation functional. Okay, so this functional will again be decomposed into different parts. So we will have the R3 part and the exchange correlation part. The R3 functional is defined as follows: 1/2 integral of the density at R1, the density at R2, divided by the interaction, the Coulomb interaction, and integrated over R1 and R2. So this is an integration in R6, if you want. And this expression corresponds to the classical repulsion, Coulombic repulsion of the charge distribution rho. Okay, so this is an explicit functional of the density, is a non-local functional of the density because it depends on R1 and R2, but it is a rather simple one, and it represents a big fraction of this functional. It's not too complicated to compute. So in practice, we are going to compute this part exactly without doing any approximations. And all the approximations that we are going to use will be in the exchange and correlation functional, for which we don't have an explicit expression in terms of the density. So what we can do, what we do very often, is to separate again this exchange correlation energy into parts, the exchange part and the correlation part. Okay, and the definition of the exchange part is, well, the expectation value of the electron-electron interaction over phi of rho. You remember phi of rho is the Slater determinant that you obtain here in this minimization for TS, minus the R3 energy. So basically, the exchange energy is what remains beyond the R3 energy for the first order energy with respect to the electron-electron interaction. And then the correlation energy is what remains. And you can write it. So if you want, this is F of minus TS minus the R3 minus the exchange. And if you recall the expression of F of rho, that was psi of rho T plus WEE, psi of rho minus TS R3 exchange, you can write it as expectation value over phi of rho of T plus WEE. Okay, and from this, in fact, you see that the correlation energy has a correlation kinetic contribution coming from this T here, the difference between the expectation value of T here and here. So this I will call it TC. And then there is a potential energy contribution to the correlation energy coming from the difference of the expectation value of this WE here and here. So this we call it usually UC of rho. Okay. And so we need to find approximations for this quantity. We can show, due to the fact that it is a single determinant, it's a simple exercise to show that the exchange energy is always a negative quantity, and also the correlation energy. From the Variational theorem, it's always a negative quantity. Okay. Any questions at this point? No? Okay. So now let me give you the Concham equation. Okay, so in practice, how are we going to do this minimization over Slater determinants? Well, we need a form for the spin orbitals composing this Slater determinant. So the spin orbital, so small phi of I, depending of x, will be chosen in the following form. So it will have a spatial part depending simply on R, and then a spin part. And in a non-relativistic theory without magnetic field, you can choose the spin part being a Kronecker delta between sigma I, which is the spin associated to the spin orbital I, and sigma, which is the spin coordinate. Okay, so I is the sigma I is the spin associated to the spin orbital, and sigma is the spin associated to the electrons, if you want, to X. And if you do that, well, you can impose very easily SZ spin symmetry. Okay. And the spatial part, well, you must have a finite kinetic energy as always. So the finite part must be a function of the first Sobolev space from R3 to C. Okay, so let's write then with this form of spin orbitals the expression of the energy here that we want to minimize. Okay, so I assume that you know how to calculate using the Slater rules the expectation value of a one-body Hamiltonian over a single Slater determinant. Okay. And so the energy, which is a functional of the of this spin orbital, I will write it like this, can be written as 1/2 sum over I to n. So first I have the kinetic part, which gives me this nabla phi of R squared dr. Okay, then I have the VNE part, so VNE, and of course, as you know, it will depend on the density, this part, and then I have the Archery exchange correlation depending on the density rho, and the density in terms of the spin orbital will be simply sum over I from 1 to n of phi I of R squared. Okay, so I assume that you can derive this. If you are not sure, this is an exercise that you should do. So this, okay, you may wonder why don't I have the Laplacian in the expression? Well, you can rewrite this if you prefer as minus phi I of R star, the Laplacian. Okay, and by an integration by parts, you can write it as this, which explains why you need simply the gradient of the orbital to be square integrable, and not you don't need some condition on the Laplacian. Okay, because of this integration by a part. Okay. Now we need to minimize this, but with some constraint, because we need to keep the orbitals orthonormal. In fact, it happens that it is enough to have the condition that the orbitals are normalized to 1. And we, we will see at the end of the calculation that the orbitals that we get will be automatically orthonormal. Or at least we can find orbitals that are orthogonal. So to have the constraint, I will use the method of Lagrange multiplier. Okay, so it means that I introduce a Lagrangian, which is also a functional of the orbitals. And then I have the expression that I want to minimize. But now I add the constraint that the integral of phi star I phi I over R is equal to 1, okay, or minus 1 equal to 0. And the Lagrange multiplier associated to this constraint, I will call it epsilon I, okay, and I have n such constraints. So I also assume that you know the method of Lagrange multipliers. And the wave function has complex values in general, and to calculate the variations with respect to the orbital, you can say it is as if the variations with respect to psi and with respect to psi star are independent. And so you can consider simply the functional derivative with respect to phi I star, and say that this must be equal to 0, and you have the same equation for phi, but this is simply the complex conjugate. So how we calculate this functional derivative? Let me review briefly functional calculus, if you are not all, well, if you need that. So let's take, so the example, if you have a function f of some variables that I will call it f1, f2, etc. Okay. Well, you know in this case how to calculate the differential of f. Okay, it will be the sum over all the variables of the partial derivative of f with respect to the variables fi, and then I have the differential of fi. Okay. Now, if you have not a function of variables, but now a functional of a function, okay, so a small f now is a function, then I can write something that looks very much the same. I can write that the variation of the functional delta f is given by the integral of the functional derivative of f with respect to the function f of x. And then I have the variation of the function f of x dx. And you see, this is exactly equivalent. So this quantity is called the functional derivative. And it is the equivalent of the partial derivative here. This is the variation of the function, and this is equivalent to the differential of the variables. But except that here we had a discrete number of variables, so we have a sum over I. But now, since a function is in fact a continuous, I mean, it's like having a continuous set of variables. Instead of summing over I, now you integrate over X. Okay. And this way of writing things is very convenient to, in practice, calculate functional derivatives. So let's do this exercise. In our case, well, the energy is quite simple because you see, so the kinetic energy parts, if you take this form of writing, is exactly in the form of an integral, and we want the derivative simply with respect to phi star. Okay, pretending that phi without star is an independent variable. So the derivative with respect to this will be simply what is left here, and you remove the integral. So it means that you are going to find minus 1 over 2 Laplacian phi I of r, okay, for this first term. Now for the second term, we need the derivative of the density, but the density, I can write it as phi I star phi r. So in fact, the derivative with respect to phi I star is simply what is left here, phi I. And then you remove the integral over r, okay? The functional derivative is what is inside the integral. So it means that the second term will be simply v ne of r times phi I of r. And now I have the functional, which is more complicated, but I will simply write it for the moment as the derivative of this with respect to phi I star. And I have the constraint here, but the constraint is easy. I take the derivative with respect to phi I star. It remains simply phi I of r with epsilon I in front. So I have minus epsilon I phi I of r. And this must be equal to 0. So that's the stationary condition for the Kohn-Sham scheme. Now, we need to have a more explicit expression for this derivative. And for this, we need yet another rule, the chain rule, that I will give you. And again, I will use the analogy with functions of several variables. So if you consider again a function f of the variables f1, f2, etc., and if the variables are in fact, in this case, each one is a function of other variables like J1, G1, G2, etc. Then if you are asked to calculate the partial derivative of f with respect to the variable f gi, then you know by the chain rule that you have to sum over all j the partial derivative of f with respect to small fj, and then the partial derivative of fj with respect to gi. Okay? That's the chain rule. Now we have an analogous expression for functional. So now if you have a functional f of a function small f, and if the function f is itself a functional of another function j, okay, and it's also a function of x, okay, but it's a functional of j, of g. Then we have a similar expression if you want the functional derivative of f with respect to g of x. It is the functional derivative of f with respect to small f of x prime, and then the functional derivative of small f of x prime with respect to g of x, integrated over x prime. Okay, and so again, it's really the analogous. So, okay, I will use that to obtain this expression. So now I can write this as, according to the chain rule, as the derivative of the functional with respect to rho of r prime, and then I take the functional, the derivative of the density with respect to phi I star, integrated over r prime. Okay. Okay. This quantity is, by definition, it's called the Archery exchange and correlation potential, and it is a functional of rho, and it is a function here of r prime. I can write it like this. Okay, or simply, to simplify notation, I will not specify that it is a function of rho. Okay, I will just say that it's a function of r. Now I need to compute this quantity. So let's do that. For this, we need to recall the expression of the density, rho of r prime. So this is sum over all electrons of phi I star r prime phi I of r prime. But you see, to calculate a functional derivative, usually we have an integral when we take a variation. And here we don't have an integral over r prime. Well, what we can do is simply to add one. So we have an integral over r prime. Let's see, we have the sum over I, integral over r prime of phi I, no, sorry, over r. I can write it like this. And then I have a delta function, r minus r prime. You agree that if you calculate this integral, you are going to replace r by r prime, and so you find exactly this expression. But now it is in the form of an integral, and so it's easy to calculate the functional derivative with respect to phi I star. Again, you see that phi I star is only here, and so all what is left in this expression is the functional derivative. So, this expression here is simply phi I of r times the delta function. The delta function allows you to calculate the integral over r prime by simply replacing r by r prime. Sorry, the reverse, r prime by r. And at the end, this derivative is simply the Archery exchange correlation potential evaluated at r times phi of r. Okay, so we replace it in this expression, and we can put this in the other side, and we finally find the Concham equation in the following form. So 1/2 Laplacian Vne of R plus R3 exchange correlation potential acting on the spin orbital phi I of R equal epsilon I phi I of R. Okay, so this is the Concham equation for giving you the Concham orbitals. And this epsilon I that started as the Lagrange multiplier associated to the normalization constraint, you see are in fact the Concham orbital energies. Okay, so this is a one electron effective Schrodinger equation giving you the Concham orbitals and therefore the Concham determinant. Okay, and if you plug that in the expression for the energy, you find the exact ground state energy, and also it gives you the density. Okay, need another page. So just to give you some notation also, so the sum of the external potential and the R3 exchange correlation potential is sometimes called Vs, the total Concham potential. Okay, and this define an effective one electron Hamiltonian that is sometimes called Hs of R. Okay, so this is called the Concham one electron Hamiltonian. So physically speaking, this is a system of n non-interacting electrons having the same ground state density as the physical system. Okay, and the role of this additional potential is to give you, well, is that the Concham orbitals gives you exactly the exact ground state density of your system. Okay, so it is a sort of a mean field to take into account the electron-electron interaction to obtain the exact ground state density. More mathematically, this Hamiltonian is a self-adjoint operator, or Hermitian if you prefer, and therefore its eigenstates form a complete orthonormal basis of the space. Okay, so you don't simply have the occupied orbitals from which we started, but you also have additional orbitals. So you have phi 1, phi 2, phi 3, etc. until phi n. So that's the occupied in the Concham determinant orbitals. But you also have phi n plus 1, phi n plus 2, in fact, until infinity. So let's put it like this. And all the rest define the virtual Concham orbitals. Okay, and the two together they form a complete orthonormal basis, or at least if you have some degeneracy, you can always find an orthonormal basis out of this space. Of the Sobolev space, if you want to be precise. And so that's why we didn't have to impose from the start the orthogonality condition. We can always find such orthonormal basis. Okay, now let me say a few words about the V-representability conditions, since it was asked. So the V-representability condition is connected with the fact that in this derivation, I have assumed at some point here that this functional derivative with respect to rho exists. Okay, but this is an assumption. Okay, and if it exists, then it defines a quantum potential or an archery exchange correlation potential. So this you can see as the V-representability condition. Okay, there must exist a V to write that. Is it true? Is it possible to always take the derivative of the functional with respect to the density? Well, it is a subtle question mathematically. But let's say that in practice, we can always assume that there is a form of differentiability for density that are close enough to the density that we care about, so that we can always define this potential. Okay. So it will not concern us in this lecture. We will assume that we can always do that. Another remark is that, in fact, the potential is defined only up to an additive constant. So you can add to this quantum potential a constant in space, and it doesn't change the quantum orbitals. Okay, because a constant in the Schrodinger equation doesn't change the quantum orbitals. It doesn't change the densities. So it is some sort of arbitrary. In practice, for atoms or molecules, for finite systems, we take this constant to be 0. So that, well, more precisely, we take the constants so that the limit when r goes to infinity of the quantum potential is 0. Okay, which is a reasonable choice to make. Now, to end with this quantum section, we can also decompose the Archery exchange correlation potential in the same way as we decompose the Archery exchange correlation functional. We can also write, of course, VHXC of R as an Archery part plus an exchange correlation potential. And the Archery part is, of course, the functional derivative of the Archery functional with respect to the density. And this is a simple exercise to check that this functional derivative is the density at R prime, and then the Coulomb interaction R minus R prime integrated over R prime. Okay, you can check that you are able to calculate that. And again, the exchange correlation potential can be separated into an exchange part and a correlation part. An important property of the exchange potential is that it decays like 1 over r at infinity. So when r goes to infinity, it decays like -1 over r. Okay, so it's sort of a long-range potential where the correlation potential decays much faster. And in particular, this property of the exchange potential is sometimes difficult to have in approximations. Okay, so that's the end of the quantum scheme. If you have any question about that, you can ask. It's clear so far? Okay, so if you don't have questions, we can continue. So what I want to do now is some extensions to that. So the Concham scheme is really the, as I showed you, the main scheme of TFT. But we can extend it. We can, in particular, explicitly include the spin. And in practice, this is important. So I want to talk about that. So this is 3.3 extension to spin DFT. So what do I mean by that? I mean that instead of having functional of the density rho, I can introduce a spin resolved densities. Okay, so what is the spin resolved density? Well, this is rho depending on sigma. So now the sigma can be spin up or spin down. Okay, and it is defined in a similar way as before. So n, I integrate the wave function x1, x2, xn squared. But now I integrate, well, I don't integrate over the spin of the first, well, if I do that, that will be sigma 1 and R1. Okay, because that's the spin of the first of x1. And I integrate simply over x2, x3 until xn. Okay, so over R3 times spin, and I do that n minus 2 times. So I have two spin unresolved density. Of course, I have rho up of R and rho down of R. And I, okay, if I integrate this spin resolved density I find the number of electron for this spin. So I will call it n sigma. Of course, the total number of electron is the sum over of the electrons of spin up and the electrons of spin down. Now, so when do we need that? If you have a magnetic field, an external magnetic field, you need this extension because now the field will couple to the spin resolved densities. If you have an open shell system, in principle, you don't need that. The theory that I have explained before is still exact for open shell systems. But in practice, it turns out that if we introduce spin resolved densities, we can find better approximations for open shell systems. So in practice, when we deal with open shell systems, we use this spin DFT. So how we formulate this spin DFT? Well, we are going to define the universal functional, but now depending on rho up and rho down. And this will be defined as follows. So we minimize over wave function belonging to the wave function space, but now with a fixed rho up and a fixed rho down. And we minimize the same expression. Okay, so now we have two constraints. And the minimizing wave function, I will call it psi of rho up, rho down. Like this. Okay. Yeah, okay, I can tell you exactly what I mean by Wn rho up, rho down. I simply means all wave function belonging to Wn so that the density up from this wave function is the same as rho up, and the density down that I extract from this wave function is rho down. Okay, so that it works the same as before. And this functional is defined for any density rho up which belong to the set of n up representable densities, and rho down must be in the set of d n down. Now we also have a Consham scheme, so we decompose f of up down into a TS of up and down. And then I will write the R3. The R3 depends simply on the total density rho. Okay, so rho is the sum of rho up and rho down. And the exchange correlation part now will depend on rho up and rho down. It's an exact decomposition. What is the definition of TS? Well, it's similar as before. We minimize over single Slater determinants Sn for fixed rho up and rho down. I will not write exactly what it means, but you guess that's exactly the same as here, but for single Slater determinants of phi t phi. And the minimizing determinant will be a functional of rho up and rho down. Okay, so that's all quite a natural extension. And we finally arrive at the expression, the Consham expression for the ground state energy as a minimum over single Slater determinants. And we are going to have, like before, the expectation value of t plus VNE. We have the R3 functional depending simply on of rho of phi. And then the exchange correlation functional that is now a functional of rho up of phi and rho down of phi. Okay, so the difference is really only this term. You can write again the stationary condition for this minimization. And I will not do it in detail, but you can, it's an exercise to do it. You can, you are going to find 1/2 nabla squared plus VNE of R plus the R3 potential. So that's the first part here. And now this term will give you an exchange correlation potential depending on the spin sigma of R. And this will act on the spin orbital that has spin sigma. So now I change my notation. I will explicitly include the spin of the spin orbital I in the notation, like this. Previously, it was included in the notation. Now, this is only the spin orbital having spin sigma. And this will be the energy I sigma and phi I sigma of R. Okay, so now you have two types of Consham equations, one for each spin. Okay, this potential is simply the functional derivative of the exchange correlation expression with respect to the spin sigma density. But obviously the functional depends on both rho up and rho down, so this will couple the two spins. And also I can give you the expression of the density, rho sigma. It will be the sum over the n sigma electrons for spin sigma of phi I sigma squared. Okay, so you have that, and of course you can define in the same way. You can separate the exchange correlation into an exchange and a correlation contribution, which has exactly the same definition as before. And one nice thing is that there is a connection between the spin-independent exchange functional and the spin-dependent one, which is called the spin scaling relation, which is the exchange, the spin-dependent exchange functional is 1/2 the exchange, the spin and the spin independent evaluated at twice the spin up density plus the spin independent exchange functional, which is evaluated at twice the spin down density. Okay, so this, in this expression, this is the exchange functional that we used before, the spin independent one. And this is, of course, the spin dependent one. So this expression is very convenient because if you have an approximation for this spin-independent exchange functional, then immediately you have the corresponding approximation for the spin-dependent case. Okay, so in practice, this is what people usually do. They develop approximation for the spin-independent exchange, and then they apply this expression to obtain the corresponding approximation for the spin-dependent case. Unfortunately, we don't have such an expression for the correlation functional. So in this case, you really need to develop from the start, for example, the approximation for the spin-dependent correlation functional. Okay, so that's about all I want to say for the spin-dependent case. Okay, and then another extension of the Consham scheme that I want to talk about, and which is very important in practice, is the so-called generalized Consham scheme. So let me write about that now. So this must be, yeah, okay, so this is 4. Generalized Consham scheme, which is known as GKS sometimes. Okay, and it is quite important because in practice, most of the calculation in DFT, I would say, in chemistry, are not done, in fact, within the Consham scheme, because we use functionals that contains very often a fraction of Hartree-Fock exchange, the so-called hybrid approximations that you probably heard about. And in this case, you have a non-local potential coming from the Hartree-Fock exchange, and so they do not belong exactly to the Consham scheme, but to the generalized Consham scheme. So let me explain this extension. So one way of explaining this is to say, okay, I have the universal functional f of rho, and and in the Consham I decompose into TS and exchange and correlation. But now I can do another decomposition. I can do the following decomposition. I can minimize over a single Slater determinants having the density rho of the expectation value of T. And then I add here in the expectation value, or well, in the expression depending on phi, I'm going to add the R3 functional depending on rho of phi. Well, this doesn't do anything because it really depends on rho, so I can take it out if I want. But what is new here is that I'm going to add a functional that I call S of phi. Okay. And then I will have a complementary functional that I will call S bar of rho. So that I obtain really the correct f of rho. Okay, so this S of phi can be any functional of the Slater determinant phi leading to a minimum in this expression. And in practice, for hybrid functional, hybrids functionals, we choose S of phi to be a fraction A of the Archery-Fock exchange energy, which is a functional of the Slater determinant. Okay, but that's only one possibility. You can have, in fact, an infinity of possibilities for this functional. And okay, and now you can obtain the equivalent of the Concham scheme. If you insert that in the original expression, you can compute the exact ground state energy by minimizing with respect to all Slater determinant. And now you are going to have phi plus T plus VNE. You have the R3 evaluated at rho of phi. And you are going to have this S of phi. And now I can put this S bar that will be evaluated at rho of phi. Okay, and this defines, if you want, another exchange correlation functional that will depend on S, and it will be a functional of phi. Okay. So you see that in this respect, the Concham scheme was only a special case. Okay, the Concham scheme is recovered. The Concham scheme corresponds to the case where S equal to 0. In this case, you don't have a functional of phi, you simply have a functional of the density, and this is the complete exchange correlation functional. But you have a lot of freedom to have any functional of phi that you want here. Okay, and then you may wonder, okay, what are the equivalent of the Concham equation? Well, if you do the minimization, you can show that you are going to find the following equation. So you have the Laplacian, the VNE of R, the R3 potential, and then so the S bar will give you a local potential as before. So I will call that V of S bar of R. So this will act on phi of I of R. Okay, but then the new term here is this one. And because it is not a functional of the density, but a functional of the Slater determinant, you will have a term that is more complicated. So that I can write as the derivative of S of S with respect to phi I star with respect to R. And this will, for example, for the case of the Archery-Fock exchange, it will give you a non-local potential. Okay. We will see that in part 2 if we have time. And so this is called the generalized Concham equation. Okay, which is in practice again what we actually use for this hybrid approximation. So it is important. There is a question in the chat. Is that S of phi used to represent other effects such as van der Waals forces? Well, here I had in mind more the exchange part, so the van der Waals are not included. To include the van der Waals, you will need to have also S of phi, which includes some correlation effects. Okay. So in fact, an extension of the hybrid functionals are the double hybrid functionals, where you have also a fraction of MP2 correlation in the functional. But in this case, you don't have a variational principle, so you cannot really see that as a functional of phi. Okay, but in principle, you know, if you have good idea about functional S of phi that gives you an approximation for the van der Waals interaction, you could do it. Okay, so. So this is basically what I wanted to do. So do you have any questions at this point?
So Julien, maybe I can ask a question.
Yes.
Yeah. So I have a question about spin DFT. So there is no magnetic field, of course, in your Kohn-Sham equation. So is that a problem, or because you mentioned the motivation, in principle, this spin resolved densities appear naturally if you had a magnetic field, but in fact, if you look at open shells, there is no magnetic field. Still, you solve the Kohn-Sham equations like that. So
no, as far as I'm aware, there is no fundamental issue about not having a magnetic field and still having the spin densities. You can have them, at least if you do it in a constraint such approach like this one. You know, it's simply another constraint that you add in the definition functional. I don't see any problem. Yeah.
Okay, thank you.
Other questions? So I have a, you know, if we either we stop here, or I can have a few things I can add if you are interested in 5 minutes, or it is as you want. What do you think, Emmanuel? Or?
Yeah, yes, if you want. So Clotilde, to answer your question, the slides are already on the website. I mean, the lecture material, where the videos are. You can just download them. Yeah, go ahead, Julien, if you want to add something.
So a little bit more. Okay, so about self-interaction, because I think that was Vincent who mentioned self-interaction. It was discussed in the Archery fork. So yeah. So let's say this is 4, 5. Okay, so if you apply, if you consider one electron systems, okay, then you only have one occupied orbital, and then it's easy to show that the exchange energy for one electron system must be the opposite of the Archery energy for one electron densities. Okay. And also, obviously, the correlation energy for one electron system must be 0. Okay, so these are important constraints that in practice tells you that in fact, when we calculate exactly, when we add exactly this archery part, in the case of one electron system, it is only a spurious interaction, and it must be compensated by the exchange part. So if you don't use any approximation for the exchange as in archery-Fock, it's not an issue. This constraint is exactly valid, and you will not get any self-interaction error. But in DFT, you know, you remember that I told you that we calculate the archery part exactly, and we use an approximation for this part. And so in this case, this constraint, and also we use an approximation for this part. And so, so in practice, with most of the approximations, we are going to have an error coming from the fact that the exchange expression does not exactly cancel the archery energy, and the correlation energy is not exactly zero. Okay, so this leads to a self-interaction error. This is also, we can also, this is also true for two electron system, for two electron in a single orbital. Okay, then you can also check that the exchange energy for two electron system in a single orbital, so the spin are opposite, I will write it like this, must be 1 minus 2 times the archery functional evaluated with the same density. Okay. And also in this case, the archery energy that we calculate exactly introduces a spurious self-interaction that needs to be cancelled by the exchange part. Okay. Of course, this is not limited to one and two electron systems, because in many electron systems, you also have some parts of the system where you almost have one or two electrons. For example, if you have a lone pair in the molecule, then it is approximately a two electron in a single orbital region. And so approximately in this region of space, you must have this constraint, okay? And also if you consider radical, for example, you have an unpaired electron, and it is approximately, at least in some region of space, this constraint that you should impose, okay? So in practice, it is very important for more than one or two, for more than one and two electrons. Okay, so that's about it. So next week we will continue, and we'll focus on the expressions for the exchange and correlation functional and its approximations.
Thank you, Julien. Thank you very much.